The universe is expanding, but it will not do so forever. We are going to uncover the ultimate fate of the cosmos in a journey to the end of time itself. By the finish, you will gain a profound new perspective on existence, from the fate of atoms to the final meaning of time. We will investigate how a silent force called dark energy could tear everything apart, and whether a great collapse might reverse creation itself. What single question about our universe's destiny feels most urgent to you? Think of the universe as a giant balloon with galaxies painted across its surface. As the balloon inflates, each dot moves away from every other dot. This simple image captures the essence of our expanding cosmos. It was Edwin Hubble who first confirmed this staggering reality nearly a century ago, observing that distant galaxies are all rushing away from us. But here is the crucial part we often miss. It is not that galaxies are simply flying through a static, empty space. The fabric of space itself is stretching, carrying those galaxies along like raisins in a rising loaf of bread. To measure the speed of this cosmic growth, scientists use what is called the Hubble constant. This is not a physical constant like the speed of light, but a value that tells us how many extra kilometers per second a galaxy appears to move away for every megaparsec it is farther from us. A megaparsec is an almost unimaginable distance, about 3.26 million light-years. For decades, astronomers have painstakingly refined this number, and their findings led to a Nobel Prize-winning discovery. The expansion is not slowing down as you might expect from the pull of gravity. It is speeding up. Something is actively pushing the universe apart, a mysterious presence we call dark energy. This relentless, accelerating expansion is the engine driving our cosmic story forward, making the ultimate fate of everything hinge on a single, profound question. What happens when this engine finally stops? Dark energy is the ghost in the cosmic machine, an invisible pressure that pushes the universe apart. Its discovery in the late 1990s was a complete shock to astronomers. They were observing a specific kind of stellar explosion, a supernova, to measure how much the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The most distant explosions were fainter than expected, meaning they were farther away than anyone had calculated. The expansion was not slowing at all. It was accelerating. This was like tossing a ball into the air and watching it fly away faster and faster, defying gravity itself. The only explanation was a mysterious, repulsive force. We call this force dark energy. Think of it as an anti-gravity effect woven into the very vacuum of space. While gravity pulls matter together, dark energy pushes it apart. And because it is a property of space itself, as the universe expands and more space comes into existence, the total amount of this repulsive push increases. This is why the acceleration is not just continuing, it is winning. The fate of every galaxy, every star, and every atom hinges on what dark energy truly is. The simplest idea is that it is a constant force, an unchanging property of empty space, what Einstein once called the cosmological constant. In this scenario, the push never weakens. But what if dark energy is not constant? What if it is a dynamic field that can evolve, growing stronger or fading away over cosmic time? The answer to that single question determines everything. If dark energy remains steady or grows more powerful, the universe faces a specific, chilling set of futures. If it weakens, however, an entirely different destiny awaits. To understand our ultimate end, we must first grasp the nature of this relentless engine. That relentless push from dark energy sets the stage for one of the most profound possibilities for our cosmic end, a fate known as the Big Freeze. Picture the very last star in the universe. After trillions of years, its nuclear furnace sputters and dies, its light fading into an eternal blackness. This is not a dramatic explosion, but a quiet, final sigh. In this scenario, the universe continues expanding forever, but the expansion itself is not the killer. The true end comes from a concept called entropy, which is essentially the universe's measure of disorder or randomness. Think of it like a hot cup of coffee left in a cold room. The heat from the coffee doesn't disappear. It simply spreads out evenly until the coffee and the room are the same lukewarm temperature. At that point, no more energy can flow. Nothing else can happen. The Big Freeze is that process on a cosmic scale. Over incomprehensible eons, all the energy from every star, every galaxy, and every particle will slowly dissipate and spread evenly across an ever-growing void. The temperature of the entire universe will approach absolute zero, the point where all atomic motion ceases. In this state of maximum entropy, no work can be done. No engines can run, no life can form, not even a single thought can spark. It is a perfect, uniform stillness. Even the mightiest black holes, which once devoured galaxies, are not eternal. Through a subtle quantum process called Hawking radiation, they will slowly leak their mass away, eventually vanishing in a final, faint puff of energy. After that, there is only a thin, cold soup of particles and radiation, forever drifting apart in an ever-darkening silence. This is the heat death, a universe that has not been destroyed, but has simply and utterly run out of usable energy. It is a quiet, gradual fading into an equilibrium so complete that time itself may lose all meaning, with no events to mark its passage. But is this gentle fade to black the only option, or could the universe's final act be something far more violent and sudden? Yet that cold, silent end is not the only possibility. There exists a far more dramatic finale, one where the universe does not fade away but turns back on itself in a cataclysmic reversal. This is the big crunch. In this scenario, the relentless push of dark energy is not the final word. Perhaps dark energy weakens over time, or maybe the collective gravitational pull of all the matter in the cosmos is simply too great to overcome forever. Gravity, the great architect of cosmic structure, could ultimately become the great destroyer. After eons of expansion, the universe would begin to slow. Then it would stop, and then it would start to contract. Galaxies, which have been flying apart for billions of years, would begin a long, slow fall back toward each other. The night sky would slowly brighten as the cosmic background radiation, the leftover heat from the Big Bang, is compressed and heated. The universe would become a cosmic pressure cooker, growing hotter and denser with every passing moment. Stars would be ripped apart, and atoms themselves would be torn into their constituent particles. This is the Big Bang played in reverse, a cosmic rewinding of the tape of creation. All of space, time, and matter would be crushed back into an unimaginably small point, a singularity of infinite density and temperature. In this ultimate collapse, every galaxy, every planet, every memory, and every law of physics would be erased. It would be the end of information, of structure, of history itself. But for some theorists, this is not a true end. This singularity could be the seed for a new beginning, a rebound that triggers another Big Bang, birthing a brand new universe from the ashes of the old. This idea of a cyclical cosmos, an endless loop of expansion and contraction, offers a profound alternative to the eternal emptiness of the Big Freeze. It suggests that our entire universe might be just one heartbeat in an infinite cosmic life. But what if the end is neither a slow freeze nor a fiery crunch, but something even stranger, a fate that tears the very fabric of reality apart at the seams? The ultimate fate of the universe rests on a single, razor's edge number, the critical density. This is the precise amount of mass and energy required throughout the cosmos to provide just enough gravity to eventually bring the expansion to a complete stop. Think of it as the universe's own escape velocity. If the actual density of the cosmos is greater than this critical value, the universe is geometrically closed like the surface of a sphere. In this case, gravity wins the long game, pulling everything back together into a big crunch. If the density is less than critical, the universe is open, shaped like a saddle, and destined to expand forever into a big freeze. For decades, cosmologists have hunted for this number, aiming their most powerful telescopes at the faint afterglow of the Big Bang. Missions like the Planck satellite have mapped this ancient light with incredible precision, and the results are astonishing. They found that the universe's total density is incredibly close to the critical value. It appears perfectly flat, balanced on a knife's edge. But this simple picture of open or closed is shattered by the wild card we have already met, dark energy. The true cosmic balancing act is not just about matter, but a three-way tug of war between ordinary matter, the invisible pull of dark matter, and the repulsive push of dark energy. It is the precise ratio of these three forces that writes the final chapter. Our best measurements today suggest that dark energy makes up about 70% of the cosmic budget, tipping the scales decisively toward eternal expansion. But is this ratio truly constant, or could it change over the eons to come? The search for an answer drives astronomers to build ever more sensitive instruments, peering into the deep universe to see if the push of dark energy has always been the same. The fate of everything depends on the outcome of this delicate measurement. While the Big Freeze offers a slow, cold end and the Big Crunch a fiery reversal, a third possibility is far more immediate and violent. This is the Big Rip. In this terrifying scenario, dark energy is not a constant force. Instead, it grows stronger and denser as the universe expands, becoming an unstoppable phantom force. The acceleration would not just continue, it would increase exponentially, turning the fabric of space itself into a relentless, destructive engine. The end would not come in a slow fading of light, but in a systematic and catastrophic shredding of reality. First, the immense gravitational bonds holding galaxy clusters together would be overcome. These vast cities of stars would be flung into the deepening void. Next, the individual galaxies themselves would be torn asunder, their stars scattered like dust in a hurricane. Then, the repulsive force would turn inward. The gravity that holds solar systems together would fail. Planets would be ripped from their stars, and stars themselves would be pulled apart. In the final moments, this cosmic tearing would reach down to the most fundamental level. The forces that bind atoms together, the very glue of matter, would be overwhelmed. Every atomic nucleus would be shredded, every particle torn from every other particle. The universe would dissolve into a chaotic, disconnected sea of fundamental components, unable to ever form structure again. The key to this nightmare lies in a single number scientists call the equation of state parameter, labeled simply as W. If this value is exactly -1, dark energy is constant, leading to the Big Freeze. But if W is less than -1, the phantom energy scenario becomes possible, and the Big Rip becomes our ultimate destiny. Current observations suggest W is very close to -1, but we cannot yet rule out this more terrifying value. The potential for such a definitive, violent end adds a profound urgency to our study of the cosmos. It transforms dark energy from a curious cosmic mystery into a force that could one day unravel existence itself, leaving not even atoms as a memory of what once was. That faint cosmic static, a whisper from the very beginning, holds the answers we seek. This is the cosmic microwave background, the oldest light in the universe. It is a fossilized echo of the Big Bang, a snapshot taken when the cosmos was a mere 380,000 years old. Before that moment, the universe was a searing, opaque plasma, too hot for light to travel freely. As it expanded and cooled, the first atoms formed, and space suddenly became transparent. That first burst of light, once blindingly bright, has been stretched and cooled by 14 billion years of expansion into a faint microwave glow that permeates every cubic centimeter of space. Its discovery in 1965 was a happy accident. Two radio astronomers, Arno Penzias and Robert Wilson, were plagued by a persistent, uniform hiss in their antenna that they could not eliminate. They even cleaned out pigeon droppings, thinking that was the source. That inescapable noise, it turned out, was the birth cry of the universe, earning them a Nobel Prize. This relic radiation is not perfectly smooth. It contains tiny, ghostly patterns, ripples of temperature that vary by mere millionths of a degree. These fluctuations are the imprint of the universe's first sounds, density waves that would become the gravitational seeds for everything to come. Every galaxy, every star, and every cosmic void we see today grew from those minuscule imperfections. By mapping these patterns with exquisite precision, satellites like COBE, WMAP, and Planck have transformed cosmology from speculation into a precise science. The specific arrangement of these hot and cold spots tells us the universe's fundamental shape. It reveals a cosmos that is geometrically flat, meaning parallel lines will never meet or diverge on the largest scales. This flatness, in turn, points directly to the universe's total density, the very number that decides between a big crunch and an eternal expansion. The cosmic microwave background is our ultimate cosmic blueprint, a direct line to the infant universe that tells us not only where we came from, but precisely how the final chapter is likely to be written. But what if this blueprint is not the final word? Could our understanding of these fundamental forces be missing a crucial, hidden piece of the puzzle? Buried within the vast cosmic web of galaxies is a ghostly echo, a frozen sound wave from the universe's infancy. This echo, known as Baryon acoustic oscillations, provides a cosmic measuring tape of unparalleled precision. To understand it, we need to journey back to the universe's first few 100,000 years. At that time, the cosmos was not a silent void, but a searing, dense soup of particles and radiation. In this hot plasma, gravity tried to pull matter together into clumps, while the intense radiation pressure pushed it back out. This push and pull created vast spherical pressure waves, ripples that expanded through the early universe at over half the speed of light. These were the universe's first and loudest sounds, a deep bass note resonating through creation. Then, at the 380,000-year mark, everything changed. The universe cooled enough for atoms to form, suddenly allowing light to travel freely. This moment of transparency, the same event that released the cosmic microwave background, also froze these colossal sound waves in their tracks. Each wave was left as a spherical shell, a faint overdensity of matter with a very specific radius. That radius, about 500 million light-years across, became a permanent cosmic yardstick. Today, when we map the positions of millions of galaxies, we do not see a random scatter. We find a subtle preference for galaxies to be separated by this exact scale, a statistical echo of those ancient sound waves. It is as if the universe imprinted a standard ruler into the very fabric of its structure. By measuring the apparent size of this ruler at different distances, and thus from different eras of cosmic history, astronomers can directly track how the expansion of space has stretched our view of it. If the ruler looks smaller than expected in the distant, early universe, it tells us how much the fabric of space has stretched since then, providing an independent and powerful measurement of the Hubble constant. More critically, it allows us to trace the influence of dark energy over billions of years, testing whether its push has remained constant or changed. This fossilized sound wave confirms the story told by the cosmic microwave background, giving us a second, independent witness to the forces shaping our ultimate destiny. The silent cosmos we see today is filled with these geometric whispers, and by listening to them, we can measure the past and forecast the future with astonishing confidence. But what if our most fundamental assumptions about this cosmic engine are wrong? What if dark energy is not the only player in this grand finale? A specific kind of stellar death provides our most direct evidence for the cosmos' accelerating end. When a dense stellar corpse known as a white dwarf siphons too much material from a companion star, it crosses a critical mass threshold and detonates in a cataclysmic explosion. This event is a Type 1, a supernova, a blast so predictable and brilliant that it outshines an entire galaxy, but its true value lies in its consistency. Because these explosions always happen at the same critical mass, they always release roughly the same amount of light, achieving a nearly identical peak brightness. This makes them what astronomers call a standard candle, a cosmic milepost of known intrinsic luminosity. Imagine you are in a vast, dark field, and you see several identical 100-watt light bulbs placed at unknown distances. The one that appears faintest is obviously the farthest away. Astronomers do the same with these supernovae. By comparing the known, true brightness of the explosion to its observed, dimmed brightness from Earth, they can calculate its distance with remarkable precision. In the late 1990s, two independent teams were using this very technique to measure the distances to far-flung supernovae. They were not looking for dark energy. They were trying to measure how much the universe's expansion was slowing down due to gravity's pull. Their results, however, delivered a shock that would redefine cosmology. The most distant supernovae, the ones whose light had been traveling for billions of years, were significantly fainter than their models predicted. This meant they were even farther away than anyone had calculated. The only possible explanation was that the universe was not expanding at a steady rate, nor was it slowing. It was accelerating. The space between us and those ancient explosions had stretched more than expected over cosmic history, pushing them to a greater distance and dimming their light. This discovery of an accelerating cosmos, driven by an unknown repulsive force, earned the researchers the Nobel Prize in Physics in 2011. It was the first direct, observational proof of dark energy's existence. Today, massive sky surveys continue to hunt for these stellar beacons, mapping the expansion rate across billions of years. Each new supernova is another data point, another check on the relentless push of dark energy, helping us understand whether its strength is constant or changing. These cosmic explosions, the deaths of ancient stars, are the very tools we use to chart the trajectory of everything that lives, right to the very edge of time. The cosmological constant was born from a simple desire for cosmic stability. When Albert Einstein was crafting his theory of general relativity, the prevailing scientific belief was that the universe was static, eternal, and unchanging on the largest scales. Yet his own equations told a different story. They predicted a dynamic cosmos, one that should either be expanding or contracting. To force his math to match the assumed static reality, Einstein introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. This was not a force in the traditional sense, but a repulsive energy woven directly into the fabric of empty space itself, a kind of anti-gravity designed to perfectly balance the inward pull of matter and hold the universe still. Then, just over a decade later, Edwin Hubble's observations revealed the universe was not static at all. It was flying apart. Einstein famously recoiled, calling the cosmological constant his greatest blunder and removing it from his equations. The irony is profound. That same discarded term, that mathematical blunder, has been resurrected as the leading explanation for the very force driving the cosmic acceleration, dark energy. The simplest model for dark energy is precisely a cosmological constant, a tiny, unchanging energy density intrinsic to the vacuum of space. Think of empty space not as truly empty, but as a seething foam of virtual particles flickering in and out of existence. This quantum jitter provides a baseline energy that exerts a gentle, persistent outward push. If this lambda is truly constant, its implications are staggering. Because its energy density remains fixed while the universe expands and matter dilutes, its repulsive influence becomes ever more dominant over time. This is the engine for the Big Freeze, guaranteeing an eternal, accelerating expansion that ultimately leads to that cold, dark, and silent end. The cosmological constant is both an elegant solution and a deep mystery. Its observed value is incredibly small, a decimal point followed by 120 zeros, then a 1, explaining why this number is so tiny and not the enormous value predicted by quantum theory, is one of the most frustrating problems in modern physics. Yet this minuscule, constant push is all it takes to set the destiny of the entire cosmos in motion, steering everything toward a final state of maximum stillness. But what if the cosmological constant is not the final answer? What if dark energy is not a static feature of the void, but something that breathes and changes? This idea is known as quintessence, a dynamic field that permeates all of space, one that could evolve over cosmic time. Picture it not as a fixed setting on the universe's control panel, but as a dial that could be slowly turning. Unlike the stubborn constancy of Einstein's lambda, quintessence is a fifth fundamental force, a cosmic chameleon capable of shifting its strength. This single possibility shatters the simple forecast of a big freeze and throws the ultimate fate of the cosmos back into question. If the quintessence field were to weaken and fade over the eons, the repulsive push holding gravity at bay would diminish. The relentless expansion would slow, then halt, and the great inward pull of all matter could finally begin, setting the stage for a big crunch. Conversely, if this field were to grow stronger, its phantom energy could accelerate the expansion beyond all limits, making a catastrophic big rip inevitable. The name itself, quintessence, is borrowed from ancient philosophy, where it referred to a fifth, pure element beyond earth, air, fire, and water. In modern cosmology, it represents that same search for a fundamental, unifying essence, one that could dictate our final destiny. Detecting this dynamism is one of the most urgent quests in astronomy. It requires measuring the expansion rate of the universe with painstaking precision across billions of years, looking for the subtlest deviations from the constant push of lambda. Each distant supernova, each map of galaxy clusters, and each ripple in the cosmic microwave background is scrutinized for a telltale sign that dark energy is not what we thought. The existence of quintessence would mean the cosmos is a far more unpredictable and dramatic place, its finale not yet set in stone. It keeps the door open to a universe that might one day collapse in on itself or be torn violently apart, reminding us that the engine driving our cosmic story may still have a few surprises left in its design. Every star that has ever shone is destined to die. The brilliant spiral of the Milky Way, the vast clouds of stellar nurseries, even the planets that may harbor life, all share this temporary status. Our cosmic era, filled with light and structure, is a fleeting chapter in a story spanning trillions of years. The ultimate fate of all this matter is locked in a cosmic tug-of-war, its final state dictated by the same expansion that defines our universe's destiny. In the long, cold silence of a big freeze, the stellar fires will go out one by one. The most massive stars will end their lives in supernova explosions, leaving behind ultra-dense neutron stars or collapsing into black holes. Smaller stars, like our own Sun, will shed their outer layers and cool for eons as white dwarfs, embers slowly fading to black. Over timescales that dwarf the current age of the universe, gravitational interactions will fling stars from their galaxies, scattering these dead relics into an ever-expanding void. The galaxies themselves will evaporate, their lights winking out. Even the black holes, the most enduring structures, are not permanent. Through the subtle quantum process of Hawking radiation, they will slowly leak their mass away, evaporating in a final, faint whisper of energy. All that will remain is a thin, ever-cooling soup of fundamental particles, drifting infinitely apart in a universe that has reached a state of perfect, useless equilibrium. Contrast this with the violent finale of a big crunch. In that scenario, the long fall back toward cosmic unity would reforge everything. The increasing heat and density would first rip molecules and atoms apart, then shatter atomic nuclei into a quark-gluon plasma, the primordial soup from which they formed. All the complex structures built over billions of years, from DNA to galaxy clusters, would be utterly erased, compressed and heated into a state of featureless unity. This dissolution of matter, whether into a cold, thin haze or a hot, dense singularity, underscores a humbling truth. The universe as we know it, with its rich tapestry of planets, stars, and life, is not the permanent state of affairs. It is a vibrant but temporary phase. We exist in a narrow window of cosmic time, long after the first stars ignited, but long before the final darkness falls or the great collapse begins. To contemplate this inevitable disintegration is to gain a profound perspective on our own moment in the light, a brief flicker of consciousness in the vast, unfolding story of everything. This vibrant era of cosmic construction is only temporary. Right now, we live in a universe where gravity is actively building, sculpting vast galaxies, and pulling them into a magnificent cosmic web. But this age of assembly has an expiration date. The accelerating expansion of space, driven by dark energy, is fundamentally changing the rules of the game. As the universe continues to grow, the vast distances between galaxy clusters will stretch at an ever-increasing rate. Eventually, these voids will become so wide and the clusters so far apart that the gentle, persistent tug of gravity will no longer be able to overcome the stretch. The signal to pull together will be lost, like a shout across an ever-widening canyon that can no longer be heard. At that point, the growth of the largest structures in the universe will simply stop. The cosmic web, that beautiful filamentary network of galaxies, will freeze in its final configuration. It will be a fossil, a snapshot of gravitational architecture locked in place for all time. But this is not a stable ending. With the expansion relentless, the individual threads of this frozen web will begin to drift apart. Galaxy clusters, then individual galaxies, will become isolated islands in an ever-darkening sea of nothingness. The raw materials for new stars, the vast clouds of gas and dust, will be pulled so far apart that they can never coalesce again. The birth of new stars will cease entirely, and the universe will transition from a period of vibrant construction to one of long, slow decay. This cessation of growth is one of the most significant milestones on the road to the end. It is the moment the universe stops building and begins its long, final journey toward silence. Even the atoms that form the bedrock of reality may not be eternal. Deep within the heart of every element, the proton has long been considered a stable, permanent fixture of the universe. But our most advanced theories of particle physics suggest this is an illusion of our brief timescale. Most grand unified theories, which attempt to merge the fundamental forces, predict that the proton itself is unstable. It should, over an almost unimaginable timescale, spontaneously fall apart. The half-life for this decay is theorized to be around 10 to the 34 years, a number so vast it defies comprehension. To put that in perspective, the current age of our universe is only about 10 to the 10 years. This means we are witnessing the universe in its very first fleeting moments, long before the most fundamental processes of decay have even had a chance to begin. In the cold, dark expanse of a big freeze universe, trillions of years after the last black hole has evaporated, this slow disintegration would become the final act. One by one, the protons at the core of every remaining atomic nucleus would rupture. The very building blocks of all matter that escaped gravitational collapse would simply vanish. An atom of hydrogen, the most common element, would cease to exist as its single proton transforms. It would not decay into other atoms, but into lighter, more fundamental particles. The most likely products are a positron and a neutral particle called a pion, which itself quickly decays into pure energy in the form of gamma-ray photons. Over these epic timeframes, all complex matter would slowly and inexorably dissolve into a faint, diffuse sea of leptons and light. The universe would be left with no solid structures whatsoever, not even the ghost of an atomic nucleus. This is the ultimate desolation, a cosmos where not only has all activity ceased, but the very potential for structure has been erased at the most fundamental level. The confirmed observation of a single proton decaying would be a monumental discovery, providing direct evidence for physics beyond our current standard model and revealing the ultimate fate of all tangible things. It would mean that every mountain, every planet, and every person is, in the most profound sense, temporary. The slow erosion of matter itself ensures that the final state of the universe is not just cold and dark, but utterly empty, a perfect void where even the memory of substance has faded into radiation. Our current cosmic spring, filled with starlight, is merely the opening scene. The universe has designated this period of active star formation the stelliferous era, and it will be its most vibrant chapter. But even this era has a limit, lasting for perhaps 100 trillion years until the very last red dwarf star exhausts its nuclear fuel and fades to black. What follows is a descent into darkness on a scale so immense it crushes ordinary comprehension. We enter the degenerate era, a time dominated by the cold, dead remnants of stars. White dwarfs and neutron stars will be the primary inhabitants, slowly cooling over trillions upon trillions of years like embers in a cosmic hearth. Following that, the black hole era will commence, where these gravitational monsters are the only significant structures left, even they are not permanent. Through Hawking radiation, they will evaporate, with the largest taking around 10 to the 100 years to vanish. If the proton decays, the final dark era begins, a near-infinite stretch of time where the universe is little more than a dilute sea of fundamental particles and radiation, expanding forever into absolute cold and stillness. To grasp these durations, consider that the entire 13.8 billion year history of our universe, from the Big Bang to today, is less than a single heartbeat compared to the eons that lie ahead. Our entire existence, from the first star to the last thought, occupies a fleeting sliver of cosmic time, a brilliant but momentary spark in an unimaginably long and fading twilight. This grand timeline reveals a humbling truth. The end of time is not a singular event we can point to on a calendar. It is a drawn-out process of dissolution, a slow fading of all activity, structure, and energy over durations that defy every intuition we possess. We are living in the universe's spectacular but astonishingly brief youth. This grand cosmic timeline, spanning trillions upon trillions of years, inevitably turns our gaze inward. The potential for a final, irreversible state forces a confrontation with questions that have haunted humanity for millennia. If every structure, every memory, and every trace of information is ultimately erased, can anything we do truly hold lasting significance? The different endings we have explored are not just physical forecasts. They are profound philosophical narratives that shape our very understanding of existence. A cyclical universe locked in an endless loop of big bangs and big crunches suggests a kind of eternal recurrence. In this model, every moment, every triumph and tragedy might replay an infinite number of times. This idea offers a strange form of immortality, but also a potential prison of endless repetition. Conversely, the silent, cold finale of the heat death presents a starkly different reality. It implies a universe with a definitive end, a final state of maximum disorder from which no new beginning can emerge. This is a one-way street to oblivion, where every achievement and every life is ultimately rendered transient against the backdrop of an eternal, featureless void. These models challenge our deepest intuitions about time, purpose, and the nature of reality itself. Is time a linear arrow flying toward a definitive end, or a circle without beginning or end? Does the erasure of our legacy at the end of time negate its value in the present moment, or does it make our fleeting existence here and now all the more precious? Scientists and philosophers grapple with these questions side by side, for the study of the cosmos's ultimate fate is not merely a technical pursuit. It is a profoundly human one, a mirror that reflects our own search for meaning against the vast, indifferent canvas of the universe. This reflection connects the grandest scales of cosmic destiny to the intimate scale of our own lives, asking us what matters in a world that may not remember us. Yet even that final, perfect stillness might not be absolute. The vacuum of space, in its ultimate cold and emptiness, is not a true void according to quantum mechanics. It seethes with a faint residual energy, a ghostly fizz of activity governed by the Heisenberg uncertainty principle. This fundamental rule of the quantum world allows for a temporary loan of energy, permitting pairs of virtual particles to spontaneously flicker into existence for an immeasurably brief moment before they annihilate each other and vanish back into the nothingness from which they came. In the heat death of the universe, trillions upon trillions of years after the last star has died and the last black hole has evaporated, these fleeting quantum fluctuations would become the only events in an otherwise timeless cosmos. They would be the sole punctuation in an endless sentence of nothing, and it is here, in this realm of the infinitesimally small, that a potential loophole to eternal darkness emerges. A concept known as quantum tunneling suggests that even the most stable, lowest energy state is not perfectly secure. Given an almost infinite amount of time, a random quantum fluctuation could, by sheer chance, tunnel through an energy barrier. Instead of creating a simple particle pair, this event could trigger a localized bubble of false vacuum, a patch of space with a different fundamental energy. If conditions were just right, this bubble could undergo an explosive inflationary expansion, birthing an entirely new universe in a fiery event that would look, from the outside, exactly like a new Big Bang. This speculative idea is often called cosmic resurrection, a phoenix rising from the ashes of a dead cosmos. It proposes that our own universe might be the offspring of such a random quantum event in a long-dead predecessor. While this remains a highly theoretical possibility, it offers a profound shift in perspective. It suggests that the end of time may not be a permanent state, but merely a dormant phase in an unimaginably long cycle of death and rebirth, where the potential for a new beginning always lies hidden within the fabric of nothing itself. Black holes appear to be the ultimate cosmic shredders, consuming everything that crosses their event horizon. But this simple picture conceals a deep and troubling mystery that strikes at the very heart of physics. When matter falls into a black hole, it carries with it a vast amount of information. Every particle has a specific type, a spin, a position, a history. According to the bedrock principles of quantum mechanics, this information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This is a fundamental rule of our reality. Yet, Stephen Hawking's revolutionary work revealed that black holes are not entirely black. They slowly leak a faint glow of radiation, now known as Hawking radiation, and over eons, this process causes the black hole to lose mass and ultimately evaporate completely. Here lies the paradox. Hawking's original calculations suggested that this emitted radiation was entirely random, carrying no information whatsoever about what fell in. It was pure thermal noise. If the black hole vanishes, leaving behind only this featureless radiation, then all the intricate information about the stars, planets, or books that fell into it would be permanently erased from the universe. This is the black hole information paradox, and it means that our understanding of gravity and quantum mechanics must be incomplete. One of these foundational pillars of physics would have to break. For decades, physicists have wrestled with this. The leading idea for a resolution suggests that the information is not lost. It is somehow encoded onto the event horizon itself, the point of no return, and then slowly and chaotically released back into the universe through the Hawking radiation. The black hole, in this view, acts like an incredibly complex scrambler of information, not a destroyer of it. This might seem like an abstract debate, but its implications for the end of time are staggering. Consider the Big Crunch, where the entire universe collapses into a single point, a singularity not unlike the heart of a black hole. If information can be lost in a black hole singularity, then it could be lost in this final cosmic singularity, erasing the entire history of the universe in one final act of oblivion. The fate of every particle, every life, and every memory would be rendered meaningless. Conversely, if the laws of quantum mechanics hold firm and information is always preserved, even through a singularity, then the story of our cosmos might somehow survive its own dissolution. The resolution of this paradox is not just about black holes. It is about whether the universe itself has a memory, and whether anything we call history can truly last forever. Perhaps our entire approach has been looking at the problem backward. We have filled the cosmos with invisible, mysterious substances to explain its behavior. But what if the culprit is not what is missing, but the very law we thought we understood? This is the radical proposition of modified Newtonian dynamics, or MND. It suggests that our theory of gravity, perfected by Newton and refined by Einstein, might simply break down on the immense scales of galaxies and beyond. Instead of invoking dark matter to explain why stars at the edges of galaxies orbit too quickly, or dark energy to explain the accelerating expansion, MND proposes a simple tweak. It posits that gravity operates with a different strength when its pull becomes exceptionally weak, a threshold crossed in the sparse outer reaches of galaxies. Imagine a car that, instead of slowing down as it runs out of gas, suddenly finds a new gear and accelerates. Mann suggests that gravity, in the realm of extreme faintness, does not fade away as our current equations predict. It holds on just a little bit stronger. This single adjustment can remarkably explain the observed rotation of hundreds of galaxies without needing a single particle of dark matter. The implications for the universe's ultimate fate are profound. If Mund or its more complex relativistic extensions are correct, then the cosmic tug-of-war is fundamentally different. The repulsive push we attribute to dark energy might instead be a subtle long-range effect of gravity itself, a gentle nudge baked into the fabric of space-time that only becomes apparent across billions of light years. This could mean the acceleration is not driven by a phantom energy field, but is an inherent property of gravity on the grandest stage. In one version of this idea, the acceleration could be permanent, locking in a big freeze. In another, this modified force could eventually reverse, pulling the universe back together in a grand crunch. These theories are not yet the mainstream. They struggle to explain all the evidence, such as the specific patterns seen in the cosmic microwave background, that are beautifully accounted for by dark matter and dark energy. Yet their persistence is a vital force in science. They are the necessary rebels that challenge a comfortable consensus, forcing cosmologists to double-check every assumption and every measurement. The very existence of these alternatives is a powerful reminder that our map of the cosmos is still being drawn. The final chapter of the universe is not yet a foregone conclusion written in the ink of dark energy. It might yet be rewritten by a deeper understanding of the most familiar force in the cosmos, the gentle pull that holds our feet to the ground and shapes the destiny of everything. Our own universe's grand finale might be a purely local affair. The theory of eternal inflation paints a picture far grander and more humbling than a single cosmic story. It suggests that the rapid, exponential expansion of space we call inflation did not stop everywhere at once. Instead, it ceased in one tiny patch, a single bubble that became our entire observable universe. Beyond the boundaries of our cosmic horizon, the inflationary vacuum continues to rage eternally, a frothing sea of hyper-expanding space. Within this chaotic sea, new bubble universes are constantly nucleating, like bubbles forming in a vast, boiling pot of water. Each of these bubbles is an entire cosmos, pinching off from the inflating background and potentially developing its own unique set of physical laws and fundamental constants. In one bubble, the strength of gravity might be 1,000 times stronger, making stars burn out in a flash. In another, the nuclear forces might be too weak to form atoms at all. Our universe, with its precise, life-permitting numbers, could be just one rare and fortunate island in an infinite archipelago of realities. Within this multiverse framework, the end of time loses its absolute finality. The death of our universe, whether by freeze, crunch, or rip, is merely the closing of a single chapter in an endless library of existence. While our cosmic bubble faces its own destiny, the greater multiverse continues its relentless, eternal creativity, giving birth to an infinite number of new beginnings. This perspective transforms the meaning of our own demise. The extinction of all light and life here does not spell the end of everything. It is simply the conclusion of one experiment in physics, one story among an infinite number of others still being written. This offers a strange form of cosmic immortality. Even as our own world grows cold and dark, the grand tapestry of existence continues to weave itself in ways we cannot possibly imagine, ensuring that the potential for life, consciousness, and wonder persist somewhere forever. Time itself may be the final casualty of the cosmic end. We think of it as a relentless river flowing from past to future, but this arrow of time is not a fundamental law of physics. It is an emergent property, a consequence of the universe's journey from a state of high order to one of maximum disorder, from the dense, hot singularity of the Big Bang to the cold, thin haze of the Big Freeze. This progression is driven by energy gradients, the differences in heat and concentration that power every process from a star's fusion to a human thought. In the final state of heat death, these gradients vanish entirely. The entire cosmos reaches a uniform, lukewarm temperature, when every point in space is identical, when no energy can flow from one place to another. What does forward even mean? The universe becomes a static, eternal photograph, with no events to sequence, no cause to separate from effect. The very idea of a past and a future dissolves into irrelevance. The arrow of time, having flown for trillions of years, simply has no target left. Contrast this with the fiery finale of the Big Crunch. As the universe collapses toward the singularity, the conditions become the mirror image of the Big Bang. The cosmic background radiation, once a cold whisper, is compressed into a searing glow. Matter is torn apart, and the increasing heat and density could theoretically reverse the thermodynamic arrow of time. From our perspective, falling toward that end, time would appear to run forward until the very last instant. But from an impossible outside view, the final moments of the crunch could look identical to the first moments of the bang. At that point of infinite density, the laws of physics as we know them break down. General relativity predicts that space and time themselves become singular, meaning time, as a measurable dimension, simply ceases to exist. It is not that time stops ticking, it is that the clock itself shatters. Whether the universe ends in fire or ice, the dimension that structures our entire reality and every memory we hold dear may not be a permanent fixture of existence. It is a temporary stage erected at the beginning of the cosmos and dismantled at its end. We cannot watch the universe grow old in real time, so how can we possibly forecast its ultimate fate? The answer lies in a kind of cosmic archaeology, where scientists piece together the history of the universe's expansion to project its trajectory forward. Every distant supernova, every map of galaxy clusters, and every ripple in the cosmic microwave background is a fossilized clue from a different cosmic era. By assembling these clues, cosmologists build robust mathematical models, powerful simulations that can be run forward to see which version of the end best fits the evidence we have from the past and present. It is like finding a single page from a book and using it to deduce the entire plot, from the first sentence to the very last word. This process is inherently indirect, a brilliant form of detective work where the crime scene is all of reality and the clues are written in light that has been traveling for billions of years. The case is far from closed, however. Our current evidence points strongly toward a continued acceleration driven by a constant dark energy, but the error bars on our measurements are still too large to rule out more dramatic possibilities. The phantom energy of a big rip or a fading quintessence that leads to a big crunch still linger at the edges of our certainty. To shrink these uncertainties and move from plausible forecasts to a definitive prediction, we need a new generation of eyes on the sky. This is the driving purpose behind a suite of incredible new observatories. The European Space Agency's Euclid telescope is already scanning the sky, designed to create the most precise three-dimensional map of the universe ever made. It will trace the invisible web of dark matter and measure the subtle imprint of Baryon acoustic oscillations across 10 billion years of cosmic history. Soon it will be joined by NASA's Nancy Grace Roman Space Telescope, a wide-eyed observatory that will discover thousands of new supernovae and map the distribution of millions of galaxies. On the ground, the Vera C. Rubin Observatory will perform a decade-long cinematic survey of the sky, watching for any tiny change that might reveal a crack in our current theories. Together, these missions will function as a single, coordinated instrument of discovery. Their goal is to measure the expansion rate and the growth of cosmic structure with a precision that is simply unimaginable today. They will look for the slightest whisper of change in the strength of dark energy over time, or any deviation from the predictions of Einstein's general relativity on the largest scales. Finding either would revolutionize our understanding of physics and force us to rewrite the final chapter of the cosmos. This monumental effort is not the work of a single nation or a lone genius. It represents humanity's collective curiosity reaching across the void, a global project to read our own ultimate destiny in the arrangement of distant suns. The data gathered by these telescopes is more than just numbers. It is a message from the future, a key that we are forging today to unlock the mystery of what happens when time itself runs out. This relentless search for an end we will never witness raises a profound question about our own motives. Why should any person, society, or species dedicate immense resources to understanding a future that lies beyond not just our own lives, but beyond the lifespan of stars themselves? The answer is written in the very core of what it means to be human. This is not a quest for practical gain. You cannot build a better phone or grow more food with the knowledge of proton decay. Its value is not measured in utility, but in meaning. This pursuit is a pure expression of our innate curiosity, a fundamental drive to look at the horizon and ask what lies beyond. It is the same impulse that guided the first astronomers who charted the stars and the first sailors who ventured into uncharted oceans. We are wired to seek the story of our existence, to find our chapter in the cosmic narrative. This drive has tangible, world-changing consequences. The need to peer deeper into the universe than ever before forces us to invent new technologies. The charge-coupled device in your smartphone camera, for instance, was refined by astronomers desperate to capture every precious photon from a distant galaxy. The algorithms that process vast amounts of data, from medical imaging to financial markets, were pioneered to handle the cosmic information streaming from our telescopes. This knowledge also serves as a beacon, inspiring generations to look up and wonder. A child who learns that the universe is expanding or that black holes exist might be sparked with a curiosity that leads them to become an engineer, a doctor, or a teacher. It cultivates a mindset of exploration and rigorous questioning that benefits every facet of society. On a deeper, more philosophical level, this cosmic perspective provides a powerful, unifying humility. It reveals that all of humanity, with all its conflicts and triumphs, shares a single, fragile planet adrift in a vast and ancient cosmos. Our differences shrink against the backdrop of an expanding universe. This knowledge does not diminish us, it contextualizes us. It reminds us that our time here is both fleeting and incredibly precious. The fact that we are alive during this brief sliver of cosmic time, this era of light, is a statistical miracle. This imbues our present moment with profound significance. The ethical imperative, then, is not to find an answer we can use, but to honor our unique capacity to ask the question at all. We are the universe's way of understanding itself. To cease this exploration, to turn away from the grandest questions of all, would be to deny a fundamental part of our humanity. This quest for cosmic knowledge, from the fate of atoms to the end of time, is ultimately a testament to the enduring power of the human spirit to reach for understanding, even when the answers offer no comfort, only truth. The silent, cold end predicted by physics may not be the final word. A civilization that survives for billions of years would not face the dying of the light with passive acceptance. For such a society, the end of the universe transforms from an inevitable fate into the ultimate engineering challenge. Imagine a culture so advanced that its timescales are geological, its energy needs galactic. This intelligence would see the cosmos not as a prison with an expiration date, but as a resource to be managed and perhaps even escaped. Theoretical concepts that sound like pure fantasy today become plausible survival strategies. They might learn to harness the immense rotational energy of spinning black holes, drawing power from these gravitational engines long after the last star has faded. They could contemplate the staggering project of building massive structures to shield pockets of space from the accelerating expansion, creating artificial islands of stability in an ever-expanding void. The most profound possibility involves the creation of an entirely new universe, a baby cosmos engineered in a lab. By manipulating the fabric of space-time, perhaps by triggering a new inflationary bubble, they could effectively give birth to a successor reality, ensuring that the flame of consciousness is passed on. This shifts the entire narrative of cosmic destiny. The final chapter is no longer a story written solely by the impersonal laws of physics. It becomes a story of potential, a drama where life and intelligence are not just fleeting spectators, but active participants with a role to play. The ultimate fate of everything might depend not just on the value of dark energy, but on the ingenuity and will of the minds that learn to read its meaning in the first place. The profound silence of the cosmos speaks volumes about our possible future. For decades, scientists have pondered the Fermi paradox, a simple yet haunting question. If the universe is so vast and old, brimming with billions of planets that could support life, why do we see no signs of anyone else? Where is everybody? One chilling answer is that every civilization, no matter how brilliant, eventually hits a wall. They might consume their world's resources, succumb to a pandemic, or annihilate themselves in war long before they can master the stars. But there is a more cosmic version of this great filter. Perhaps the ultimate obstacle is not a civilization's adolescence, but the universe's old age. The relentless expansion and the inevitable cooling could be a deadline that no one can outrun. Every song, every story, and every empire might ultimately be silenced by the slow, grinding engine of cosmic decay, long before any two civilizations could ever hope to meet across the interstellar gulfs. This suggests a deeply lonely destiny, where the quiet we observe today is not a temporary condition but a permanent state, a preview of the final heat death where not a single signal remains. Yet another possibility is even stranger. What if we do not see them because they have evolved beyond our recognition? A truly advanced intelligence facing a universe with a finite lifespan might not bother with radio signals or interstellar probes. Their ultimate project could be to transcend the physical limitations of their biology and their home world entirely. They might upload their consciousness into stable computational substrates, retreating into simulated realities to wait out the eons, or they may be actively working to engineer an escape from this dying cosmos altogether. In this view, the Great Silence is not a graveyard, but a library where everyone is too preoccupied with the final exam to make any noise. The search for extraterrestrial intelligence then becomes inextricably linked to our understanding of cosmology. The end of time is not just a physical process, but a potential solution to one of our greatest mysteries, forcing us to wonder if the universe is empty because it is inherently hostile to life, or because all the life that ever was has already moved on. Our most confident predictions about the cosmos rest on a foundation we know is cracked. The twin pillars of modern physics, general relativity and the Standard Model, are monumental achievements, yet each is incomplete in its own realm. General relativity masterfully describes the gravity that sculpts galaxies and bends the fabric of space-time itself, but it is silent on the quantum world. The Standard Model, meanwhile, catalogues the zoo of subatomic particles and their interactions with stunning precision, but it has no place for gravity. They are like two perfect maps, one of the ocean's currents and the other of the mountain peaks, with no chart for the turbulent coastline where they meet. The ultimate fate of the universe, especially in its final, violent moments of a big crunch or its infinite, cold desolation, pushes into territories where both maps fail. This is the uncharted frontier of quantum gravity, a theory that would seamlessly weave these two narratives into one. Without it, we are trying to forecast a hurricane using only the rules of geology. The singularities at the heart of black holes and the hypothetical moment of the Big Bang are realms of infinite density where the familiar concepts of space and time simply cease to have meaning. Our equations spit out infinities, which is the universe's way of telling us we have lost the plot. A successful theory of quantum gravity would rewrite the final chapter, not by editing a few lines, but by revealing that the entire book is written in a language we are only beginning to decipher. It could show that the universe avoids a true singularity through a quantum bounce, or that the vacuum of empty space holds a stability we cannot yet perceive. This inherent uncertainty is not a failure of science. It is its greatest strength. The core of the scientific method is built on this provisional humility, this open admission that our best models are always works in progress, awaiting the next discovery that will shatter and then rebuild our understanding. The true end of time, therefore, might not be a freeze, a crunch, or a rip, but something so profoundly strange that we lack the very concepts to describe it. So where does this leave us, standing before a gallery of possible endings for everything that exists? The evidence we have gathered, from the distant glow of supernova to the faint whisper of the cosmic microwave background, points a steady finger toward one outcome. A constant dark energy, an unchanging push, guides our universe toward the big freeze, an eternal expansion into a state of cold, dark equilibrium. This is our best forecast, the model that currently fits the data with the fewest wrinkles. Yet the other possibilities have not vanished. The fiery reversal of the Big Crunch remains a haunting alternative should dark energy ever weaken its grip, and the violent shredding of the Big Rip is a terrifying specter if that same force grows stronger over time. These are not mere thought experiments. They are the ultimate stakes written in the language of physics. A Big Crunch means a cosmic reset, a potential rebirth from the ashes of a singularity. A Big Rip is the definitive end of all structure, leaving not even atoms as a memory. Our favored Big Freeze offers a different kind of finality, a slow, inexorable fading where time itself may lose all meaning. This synthesis is not about picking a winner, but about understanding the profound sensitivity of our cosmic fate. The destiny of every galaxy, every particle, and every moment of consciousness hinges on the precise behavior of a single, mysterious component that makes up most of the universe. The journey to the end of time, therefore, narrows to a single, monumental question whose answer still floats just beyond our grasp. Our exploration reaches its end, but the cosmos itself is far from finished. We have journeyed across eons, from the first stars to the last black holes, tracing the possible fates of everything we know. The relentless push of dark energy, the silent fade of heat death, the fiery reversal of a great crunch, each one paints a universe of breathtaking scale and profound mystery. These are not just abstract ideas, they are narratives written in the language of physics, stories where the fate of every atom, the nature of time itself, and the very laws governing reality are all intertwined. We have seen how a single, elusive number, the strength of dark energy, holds the key to our ultimate destiny, a question that connects the quantum flutter of a vacuum to the grand architecture of galaxy clusters. The answers remain uncertain, hidden in the faint light of distant supernova and the frozen echoes of ancient sound waves. Yet this uncertainty is not a failure. It is an invitation, the quest to understand, to look into the abyss of time and ask what happens next. This is what defines our species. It is a testament to a curiosity that reaches beyond our own fleeting lives. Let this knowledge not be a source of despair for an end we will never see, but a wellspring of wonder for the incredible, ongoing story we are all a part of, a single, brilliant chapter in a cosmic saga still being written. We would love to hear which cosmic ending you find most compelling. Share your thoughts in the comments below and subscribe for more journeys to the edge of understanding.